Hey everybody, welcome to the CSBP meeting. I hope the out-of-towners are enjoying your time in beautiful Madison. I'm sorry I couldn't be there. Right now I'm recording this at my daughter's college orientation. Figured I'd try to get this done. The conditions aren't great here, but let's see what happens, okay? So this talk shows how you can do data fusion potentially between multiple satellites, multiple sensors, and I think the relevance to this meeting is that the NUCAPS products are derived from using JPSS data. So we want to show a novel case of using JPSS data at ideally very low latency, combined with satellite data from a European satellite and instrument. So I think it's a pretty neat idea, and it was done during the pandemic, but I haven't had time to present, and I hope that the CSPP meeting would be a chance to finally present it to live, and here I am recording it. But let's do it anyways. So for those who are not familiar with TROPOMI, it's an instrument that's on the Sentinel-5 precursor, part of the Copernicus suite of satellites. So developed by European Space Agency and the Netherlands Space Office. It measures trace gases at, I say, unprecedented resolution, because it's just a dramatic improvement over its predecessors. Mainly useful for air quality and climate monitoring, but a lot of other things. I don't think you can see my mouse movement, so what this slide is showing is if you look at this band along the edge of the Earth, you can see the electromagnetic range that is utilized to derive these products, starting with ultraviolet at the top, going down into visible, near infrared, and shortwave infrared, and then the atmospheric compositions that are derived from UV. You got ozone, sulfur dioxide, and formaldehyde at the top there. Nitrogen dioxides using a band of energy spanning from ultraviolet into visible, and then aerosols and clouds spanning the red edge there, and down at the bottom the shortwave IR energy is used to derive the carbon monoxide and methane products. Okay, so this slide shows nitrogen dioxide and compares how much better TROPOMI is with its predecessor, the OMI instrument, which flew on NASA's Aura spacecraft and provided spatial resolution of 13 by 24 kilometers. So the 7.2, I think it is, kilometer resolution along track for TROPOMI is a huge improvement over that, and so it's getting to the point now where the resolution of instruments like TROPOMI, you can compare at regional scales with sensors like the VIIRS day-night band here, and the nitrogen dioxide is representative of mostly emissions, burning of fuel from things like vehicles and power plants, basically the burning of fossil fuels. So we've got opportunities for a lot more research, just a lot more interesting research opportunities. Interestingly, TROPOMI further improved the spatial resolution of their products after the spacecraft was in an orbit by tuning the master cycle sampling period, while it's in orbit. So they are actually down to 5.3 kilometers along track for their products. And this is, hopefully you can see this animation. This is again nitrogen dioxides, and it's a 6-month animation of global NO2. So it's an interesting animation to give you an idea for the hotspots of emissions globally from fossil fuels, and basically industry, where the economies are booming, and not surprisingly, a lot of the emissions are the United States, Europe, and China, for the most part. So why use NUCAPS? NUCAPS, NOAA, Unique Combined Atmospheric Processing System. These products serve many purposes, including profiles of temperature and moisture, and again, trace gases, among other things. So products for NUCAPS are derived from instruments on JPSS satellites, ATMS and CRIS, and they're available from class, or researchers can generate their own from code developed by Nadia Smith, who should be out in the audience there somewhere. Hi, Nadia, if you're out there. I know you. Stand up and take a bow, Nadia. All right. So if you think about when data fusion is possible, and why use NUCAPS and TROPOMI, historically the impediments for data fusion are differences in spatial and temporal resolution. If the data doesn't line up temporally or spatially well enough, it doesn't have to be, there's depending on the need, you can resample spatially, and similarly, you need a certain amount of temporal resolution, otherwise you just can't do it. As far as radiometric resolution, that may not matter. In other words, what bands you need in the electromagnetic spectrum, you may want the same range, you may want different ranges. So that's really depends on what you're trying to do, okay? If you're generating an RGB, then obviously you want 3 different bands, but in this case, we want the same energy range. So here's the deal. TROPOMI and SUMI NPP happen to have temporal synergy. What ESA did is they intentionally put the Sentinel-5 precursor in what's called a loose formation, 3.5 minutes behind SUMI NPP. So it's the exact same orbit, just running 3.5 minutes behind. So why would you do this? You might want to do this if one sensor produces a product that the other can leverage to a great advantage, and that was the case here. ESA realized that if they could utilize the much better cloud mask product from VIIRS on SUMI NPP, then that will greatly improve some of the products that TROPOMI is producing. And there may be other reasons. The data products of one sensor may help validate products from the other, and of course, you now have the potential for fusion products, because the whole temporal difference problem is solved for you. Okay, so, and as far as the spatial resolution differences, as long as they're not that great, at Space Science, these are the problems that we're good at, where we have no problem resampling and reprojecting data. We do this all the time, and in this project, we use the SatPy library, and I leaned on Dave Hayes to use their experimental multi-scene. we experimented and we pushed it, and it was very useful. So for this experimental product, this was actually Brad's idea. So as you can see, I get really no credit for anything novel here. This was one of Brad's ideas to focus on total column CO, because he realized, again, I wouldn't have known this, on my own, but he realized that NUCAPS is very most sensitive to middle tropospheric CO2, and he surmised that a very simple difference product, just take TROPOMI total column minus NUCAPS total column, and that should highlight boundary layer CO detections. And such a product would have great value for improving air quality forecasts and situational awareness during wildfire events. Okay, so how did we do this? Again, I leaned heavily on and also contributed to SatPy. I actually wrote the TROPOMI reader for SatPy during a week-long developer conference. In fact, I should give Jeff Curitan some credit, who's also out there somewhere probably, because he sat next to me and I kept poking him, hey Jeff, how do you do this? And he helped me with some of the coding on that TROPOMI reader. For data sources, NUCAPS science EDRs can be generated, and we do this at SSEC, and TROPOMI can be obtained from NASA, the Earth Observatory, and there's also a nice Copernicus open access hub. The model is very simple, and this could be automated easily. This is just what I like to do for this type of processing, just for every logical time interval, whether it's a day or hour or whatever. Just grab the data you need. If you can get it quickly with low enough latency, do whatever processing you need to do, nuke that data, and just keep iterating. And if we have the luxury of, like we do at Space Science, of having the bandwidth to fetch data easily, then why not? Just chug along that way. So I gloss over the processing data part because if you want, you can just look at my code, which I always like to make publicly available, so you can comment and criticize, and all that stuff makes it better, and it's available on a SSEC GitHub library. Did I mention? Okay, I'm trying to remember something I think I might have glossed over, but anyways, the results of this were pretty promising. On the left here, you see the TROPOMI total column CO product, and on the right, you see the NUCAPS total column CO product. I guess what I was going to mention is that for that NUCAPS product, I actually had to adapt some IDL code Brad Pierce wrote to integrate the pressure levels for NUCAPS. So that's in that repository, the adaptation of that to Python and leveraging SatPy. We focused mostly on a case study on the day of July 19th, 2019, because there was some large wildfire events that we thought would be a really good case study day, and you can see those up in Canada and Alaska. And the difference product did very clearly highlight those wildfire hotspots. So we were really happy with the outcome of this experimental product, and it did nicely align. Very good coincidence with VIIR's true color imagery. You can see the smoke signatures there that I've circled, and also very good alignment, nicely spatially coincident with active fire detections on that same date. So this, in summary, I guess the point here is this project demonstrated the promise of TROPOMI JPS data fusion, and in my view, the next steps for something like this would be to automate this process and make these products publicly available. And we tried to do that next step. Jim Davies and I worked really hard on a proposal for JPSS Proving Ground, and it made it to the final cut, but it was not selected. And so we do feel that this was kind of a novel demonstration of very simplistic but a useful demonstration of multi-sensor data fusion between two different satellites that could produce a product that would be of particular benefit to National Weather Service incident meteorologists to provide better estimates of the vertical distribution of pollution from wildfires. We think this would be a useful product, and hopefully it's a good example of some of the things we can do going forward with low latency JPSS data. Thanks for your time. Enjoy your time in Madison, and we'll see you soon, hopefully. Take care, everybody.